This session is about taking a look at some of the slope W background and some of the slope W formulations. Limit equilibrium method of stability analysis is the oldest and best known numerical technique in geotechnical engineering. The idea of dividing a potential sliding mass into slices dates back to the early 1900s. To my knowledge, the first documented use of the method of slices is the analysis of the 1916 failure at Stigberg Quay of the Stigberg Quay in Gothenburg, Sweden. The case history is published by Patterson in Geotechnical in 1955. The title of the article is The Early History of Circular Sliding Surfaces. Here is a cross-section of the failure. Notice the circular sliding surface and the profile after the slide, profile before the slide. And so obviously this structure failed, and there was interest in trying to attempt to analyze this failure using the method of slices. Here's a picture of how the sliding mass was divided into slices, and we see that this idea of dividing into slices and resolving the forces on the slices dates back a long time and has been with us for a long time, almost a century by now. Initially, all interslice forces were ignored. This made it possible to do analysis by hand. And by ignoring all the interslice forces, the method became known as the ordinary or Finite method. Later in the 1950s, Bishop added interslice normal forces and satisfied overall moment equilibrium. This became known as the Bishop simplified method. Very much at the same time, or close to the same time, Yan Bu also considered interslice normal forces, but satisfied overall horizontal force equilibrium. This has become known as the Yan Bu simplified method. Adding the interslice normal forces led to the need for an iterative approach to finding the factor of safety. This is doable by hand, but only for a limited number of trial slip surfaces. Any of you who have taken some graduate courses in geotechnical engineering have in all likelihood had to do this by hand or through the use of a spreadsheet. Later, the advent of computers in the 1960s made it possible to more readily handle the iterative procedures inherent in the method, and as a result this led to mathematically more rigorous formulations. For example, the Spencer or the Morgenstern-Price methods. These methods include both interslice normals and interslice shear forces and satisfy all equations of statics. The introduction of desktop computers in the 1980s made it viable to develop commercial software packages based on the limit equilibrium formulations. Slope W is just one example of the commercialization of the technique. Today, this type of software is so common that it is now routinely used in geotechnical engineering practice, and I would venture to say that all geotechnical consulting firms have some form of a piece of software that allows them to analyze stability using the limit equilibrium formulation type of a method. Interestingly, in spite of the extensive use in practice, the fundamentals are generally not well understood. For example, the fact that the method of slices is based on nothing more than statics is often forgotten. Also, the fact that all of the slices have the same factor of safety, and what this means in the formulation is usually not appreciated. To use the limit equilibrium method effectively, however, it is useful to have a good understanding of the formulation fundamentals. And in the next few slides, I'm going to highlight some of these fundamentals and give you a reference to more details. Slope W formulation is based on the principles of limiting equilibrium. This means forces on a free body are such that it will remain stationary. Stated another way means this means satisfying statics. It means the summation of moments, horizontal forces, and vertical forces must be zero. So the summation of moments about some point must be zero. The summation of forces in the horizontal direction must be zero. And the summation of forces in the vertical direction must be zero. This is at the heart of a limit equilibrium formulation. Now, to render some of these equations determinate, some assumptions have to be made. Some of the important assumptions are that the factor of safety is constant along the slip surface. That is, each slice has the same factor of safety. And this comes about from the definition of the factor of safety. The factor of safety is defined as the factor by which the soil strength must be reduced so that the potential sliding mass is at the point of limiting equilibrium. That is, the potential sliding mass and the moments and forces of the potential sliding mass must sum to zero. As I've already noted, we do not have the time here to go into greater detail, except highlight some of these main points, but I do direct you to a paper on the CD. There's a folder on the handout CD entitled Papers of Interest. In this folder there is a paper, The Limits of Limit Equilibrium Analyses. It is the 2001 R.M. Hardy lecture that I was fortunate to be invited to give. In this paper there are two issues that are of extreme importance. At the root of the method, we in essence iterate to find the forces on each slice such that 1. The factor of safety is the same for each slice, and we find the forces on each slice such that each slice is in force equilibrium. The side effect of doing this is that the resulting computed forces may not represent actual field conditions. This is one of the limitations of the limit equilibrium formulation. Fortunately, this does not invalidate the factor of safeties that we compute, as we will see at the end of this session. So, you are all likely familiar with the procedure. We take a trial slip surface and we create a free body of the potential sliding mass. The potential sliding mass is divided into slices because we cannot deal with the whole free body of the sliding mass. We divide the sliding mass into small pieces called slices, and then we resolve the forces on each slice. And so, for example, we may have the weight. We may have the normal force on the right and a normal force on the left. We might have some shear on the right, some shear on the left. We have a normal and we have some shear strength at the base of the slice. And so we must find the forces and resolve the forces in such a way that the summation of forces in the vertical and horizontal directions for each slice sum to 0. Slope W is formulated on the basis of the general limit equilibrium method. We call it the GLE method, and we will talk a lot about the GLE method in Slope W. This method encompasses key elements of many of the other methods that are commonly found in the literature. The ordinary or Fernelius method, the Bishop or Janbu simplified method, Spencer and Morgenstern Price methods, Corps of Engineers method, and even the LK method. The GLE method is based on two factor of safety equations. We have one factor of safety equation with respect to moment equilibrium, and we have a second factor of safety equation with respect to horizontal force equilibrium. The idea of using two-factor safety equations was first published by Spencer a long time ago in 1967. It is published in Geotechnical, and anybody that has had anything to do with limit equilibrium formulations is in all likelihood familiar with Spencer's 1967 paper. Here are the two factor safety equations, one with respect to moment and one with respect to force. I will not dwell here on the details of these two equations except to note that the normal at the base of the slice occurs both in the numerator and in the denominator of the equations, and the normal occurs in both the moment and force factor of safety equations. Here is the equation for the normal at the base of the slice, and it's worth spending a few moments on this equation. It is obvious that if we have a slice, that the normal at the base of the slice is a function of the weight of the slice. It's also quite readily evident that the difference in the shear on the side of the slice also affects the normal at the base of the slice. The normal is also affected by the inclination of the base of the slice. But what is most peculiar is that the normal is a function of the factor of safety. How can this be? How can a stress condition in the field be a function of the factor of safety? This is one of the peculiarities of the limit equilibrium formulation, and it does have a profound effect on the normal that we compute, and consequently it has an effect on the normal stress distribution that is computed along the trial slip surface. Interestingly, the computed distribution of the normal stress along the trial slip surfaces may not necessarily be representative of the actual stresses in the field. Also, Of course, the normal depends on which equation is being satisfied. Is it moments or is it force? Now, in the Spencer and the Morgenstern-Price methods, we attempt to find the forces such that the two are the same, and consequently the normal is the same for moment and force equilibrium. But in a Janbu simplified versus a Bishop simplified, the normal at the base of the slice might be different. Just one quick comment on interslice forces. Slope W uses this equation that says the interslice shear is equal to some function times the interslice normal times some scaling factor. F of x is a distribution or a shape function. The two most common in slope W are a constant function or a half sine function. A constant function is a straight line at 1.0. A half sine function is a half sine. Lambda is a scaling factor. It is a ratio of interslice shear to interslice normal. If f of x is 1, in other words the Spencer method, the inclination of the shear normal resultant is lambda. Put it another way, in degrees it is arctan lambda. So if we have a slice and we have some interslice normal and some interslice shear, then the angle of the resultant is lambda. Jumping ahead a bit then, we produce what we call a GLE plot. And it's a plot of factor of safety versus lambda. Lambda is a representation of the interslice shear. If lambda is 0, lambda 0, no shear. Therefore, Bishop's simplified method said that he would satisfy only overall moment equilibrium and ignore interslice shear. So therefore, the Bishop factor of safety on this plot falls on the 0 lambda axis and satisfies only moment equilibrium. Janbu's simplified method also ignored interslice shear, meaning lambda is 0, but satisfied only force equilibrium. Therefore, the Janbu simplified factor of safety falls here on this diagram. Morgenstern-Price or Spencer attempt to determine a lambda value such that the force factor of safety and moment factor of safety were the same. In other words, some form of interslice shear was required. And where the two factors of safety are the same and we come down, this is the lambda value that is required to make the two factors of safety the same. We will refer to this graph a lot, and there are several benefits in it. It shows the relationship between several different factor of safety methods, and also, as we will see later, that these curves, they sometimes can tend to become parallel, which is an indication that it is impossible to find a solution to that particular problem. But we'll come back to that later. So, The GLE plot is something that can be produced in SLOPE-W, and I will show you in a few minutes how to do that, but it provides a lot of useful information in interpreting the results. And at the end of this session, we will recommend highly that looking at results is more than looking at factors of safety. We should also look at things like the GLE plot. In summary then, with these two factor of safety equations and the assumptions that are made about interslice shear, we can create the factor of safety for all of these commonly published methods: the ordinary Orfanelius, Bishop simplified, Janbu simplified, Spencer, Morgenstern, Price, and so forth. We will now start exploring some of the details in SLOPE-W. First of all, it is in the Keyin Analyses dialog box that we select the method. Analysis type. It's right up in here, and we will do this several times. But the key point here is Keyin Analysis dialog box is where we select the method and where we select slip surface shapes and so forth. Let us then inspect the differences between some of the methods. We can demo this by opening up SLP-01, and we will start with a Spencer's method and look at the various assumptions inherent in the ordinary Bishop Janbu methods, and then we will create a GLE plot to show you how this is done. Let us go then to GeoStudio and open up file SLP-01. Once you have opened the file and you have gone to the Define view and clicked on the All Objects Zoom icon, you should see a diagram like this. Now, if we go into the Keyin Analyses dialog box, you notice that we have selected here the Spencer method. If your particular problem does not have the Spencer method, then select the Spencer method, and after you have done that, let us click on the Solve icon and resolve the problem. Now let's go to the Results view, and in this particular case, I've turned off the safety map, and I've turned off the sliding mass shading, although you can leave it on if you like. I'm going to zoom in to the area of the sliding mass, slide my diagram a little bit to the left, and introduce you to a command that you will use a lot that is called View Slice Information. And if we click on the first slice at the crest, with the down arrow, or with the arrow to the left, you can look at the forces on each slice. Now, before we do that, we'll close this dialog box, and All of the toolbars are floatable toolbars in Slope W. Currently, I'm looking at the Spencer method. I want to look at the ordinary method. Now I can go View, Slice Information, and notice how the slices have no interslice normal and no interslice shear. There are no forces here. As a consequence, you will see that we have poor force polygon closure. And if the force polygon does not close, this means that the slice is not in force equilibrium. And it gets worse as we go all the way to the point where the base of the slice is horizontal, and once we go past the point where we go to the passive end of the sliding mass, we see that the force polygon closure gets worse and worse. And this is why the method is never used in practice. We keep it here in Slope W for illustrative purposes, but it is not used in practice. Now let us go to the Bishop method. Once again, say View, Slice Information, going back to the crest again, and stepping down to the slice, just the last slice at the crest of the slope, we now see that we have interslice normals. We have interslice normal forces. Notice, however, that we do not have interslice shear. And Bishop satisfied only overall moment equilibrium, and so consequently this is the Bishop factor of safety. But do notice that we get fairly good force polygon closure. And this is true for almost all of the slices. The force polygon closure for this particular circular slip surface is actually not bad, saying that the forces on the slices are almost in equilibrium. The same holds true for the Bishop method. Say View, for the Janbu method, say View, Slice Information, and you will notice that you have interslice normal, no interslice shear, but do notice that we satisfy force equilibrium pretty good. The force polygon closure is actually quite remarkable in this particular case. Recall, though, that Janbu only satisfied overall horizontal force equilibrium. Now let us go to the Spencer method. And once again, say View, Slice Information, and once again we go to the crest, and now we see that we have both interslice normals and interslice shear. Now, in order to, before we do that, notice that we get very good force polygon closure for all the slices, and this means now that we have found the forces on this slice such that this slice is in force equilibrium, which was the objective of the exercise. To achieve this, we had to have some interslice shear, and this is the Spencer method. Therefore, the lambda value is a representation of the inclination of the resultant of the shear to normal between the slices. And we see here that the applied lambda is 0.32. In other words, the shear is approximately 32% of the normal between the slices. However, to achieve the very good force polygon closure, we had to include some interslice shear. Now let us go back to the define view. Click on Keyin Analyses, and let's change the type of analysis to GLE. And just for comparative purposes, let us select a constant function which is inherent in the Spencer assumption. So what we would be doing is again determining the Spencer factor of safety, but we will be able to produce a GLE plot. Having done that, we click on the solve icon and reanalyze the problem. Now we go back to the results view, and notice now that we are looking at the GLE factor of safety. Now when you go draw slip surfaces, you note that all of the factors of safety are listed here. The one with the lowest factor of safety is listed at the top. We'll come back to that at a later time. But there is the possibility of producing a graph here of factor of safety versus lambda. Clicking on the graph button, we obtain the graph of factor of safety versus lambda. Now if you were to take the time to check the Bishop and Yanbu factors of safety that we computed and the Spencer factor of safety that we computed, we would have the Bishop factor of safety would be here, the Yanbu factor of safety would be here, and the Spencer factor of safety is here, and the lambda value is here. And recall that lambda was approximately 0.32, meaning that is the location where the two factors of safety curves cross each other, and that is the Spencer factor of safety, because we said that we were going to use a constant interslice force function. So you can look at the different methods. You can use the view slice force information to confirm as to what interslice forces are concluded in the method, and you can produce a GLE plot, which you will do a lot for interpretation of results, which incorporates the Bishop simplified, Yanbu simplified, and the crossover point, which may be a Morgenstern Price or it might be a Spencer, depending on the assumed interslice force function. So we have explored how to look at slice forces for the different methods and see what forces are included on the slices for the different methods, and we have shown how to develop and produce a GLE graph and how to interpret the GLE graph. To this very day, many people still ask the question, what method should I use? Our recommendation and response is that you should use the most mathematically rigorous method. You should use a method that satisfies all equations of statics. That means a Spencer or a Morgenstern Price type of method. With the software now available, there is no reason to not use a fully rigorous method. There is no more work involved in defining a problem for a Spencer method than it is for a Bishop method. And if you have to, and if you are curious about the difference between factors of safety, then you can produce a GLE plot, and the factor of safety versus lambda plot can help you determine the difference between the methods if you see a difference. We will now move on to a different subject, and that is looking at various cases and on the shapes the effect of the shapes on the trowel slip surfaces. Recall that in the limit equilibrium formulation we have to make an assumption about the interslice forces. The question often arises, how important is this assumption? As it turns out, the assumption we make depends on the shape of the trowel slip surface that we are trying to analyze. Sometimes the interslice forces, particularly the shear forces, are not important, while for some cases the interslice shear forces are very important. Take a look at this case where we have a perfectly circular arc of a circle slip surface. We notice that in this case that the moment equilibrium is completely independent of interslice shear. It does not matter what assumption we make about interslice shear, moment equilibrium is not affected by interslice shear. Force equilibrium, on the other hand, is affected by interslice shear. And why is that? Well, imagine that this is a solid block. I always like to imagine something like a wood block. I can rotate this block without any slippage between the slices. As a result, moment equilibrium is independent of interslice shear because the interslice shear is not required in the rotation. However, if I were to take this sliding mass and slide it horizontally, now the sliding mass would have to contort considerably. There would be a lot of slippage between the slices, and consequently the factor of safety based on horizontal force equilibrium is sensitive to interslice shear. And this is why the Bishop factor of safety for circular slip surfaces is often very, very close to a Spencer or Morgenstern Price method, again, if the trowel slip surface is circular. The Janbu simplified is different because it depends on the interslice shear and satisfies only force equilibrium. Now let us look at a planar slip surface. Now we have the exact opposite. Moment equilibrium is now very sensitive to the interslice shear, while force equilibrium is hardly affected at all about the interslice shear. So once again, it would be easy to slide this potential sliding mass laterally without any slippage between the slices. Consequently, interslice shear is not important. However, if we were to rotate this sliding block, now the sliding mass would have to contort a lot, and there would be a lot of slippage between the slices, and consequently shear between the slices is very important. But notice that in this particular case, the Bishop factor of safety is lower than the Janbu factor of safety. All of this because of the difference in the shape of the trowel slip surface. So now we begin to see that the shape of the trowel slip surface has quite an effect on the results, and the GLE plot can help us sort out why there is a difference. Now here we have something that is a little bit more realistic. We have a tension crack, then we are on the arc of a circle, then we slide along some planar segment on top of some hard bedrock in a weak layer, and then we are back on the arc of a circle. Now in this particular case, moment equilibrium is sensitive to interslice shear, and force equilibrium is also sensitive to interslice shear. So in real-world practical cases, we should do something like a Spencer or a Morgenstern price analysis so that we include and consider both interslice shear and interslice normals, and we seek to satisfy both moment and force equilibrium. Now there's another very interesting observation about this plot, is that the Spencer, for example, is lower than the Bishop. And what this demonstrates is that simple does not mean erring on the safe side. We still hear people say sometime, I will just do a simple analysis and err on the safe side. We cannot say that. Simple does not mean erring on the safe side, and this GLE plot clearly demonstrates why that is the case. Another reason why it is useful sometimes to make a GLE plot, and in this particular case, when you do that, you can readily see why the Spencer factor of safety is lower than the Bishop factor of safety. Now we move into a block type of a trowel slip surface, and what happens with block type trowel slip surfaces, we often have quite sharp corners here, and this has quite an effect on the results and can have quite an effect in that both force and moment now become sensitive to interslice shear, and it is possible in a case like this that both moment and force become very close to each other, and sometimes we get fortuitously the wrong crossover point and get erroneous factors of safety. I won't take the time here to talk about block trowel slip surfaces, but they are useful sometimes, but they have to be used with some considerable caution because of the sharp corners here. The point is, once again, the GLE plot can help us interpret the results, particularly if the moment and factor of safety and force factor of safety curves tend toward being parallel, and they may even have several crossover points. Now here's a real life case of a real excavation in the city that I live, Calgary, Alberta, Canada. And this was a deep excavation, and there was some shoring here, a sheet pile wall. And the analyst needed to analyze the stability of the excavation, and he chose a particular slip surface shape that goes into the ground quite sharply, goes through the base tip of the wall, and comes out quite sharply. Now, interestingly for this case, if this wall or this potential sliding mass should rotate, it would have to contort very substantially. If it were to slide sideways, it would have to contort very substantially. Consequently, our force, the force curve, and the moment curve are somewhat close to each other, and now we see a very big difference between a Bishop and a Yanbu and a Spencer factor of safety, for example. In this case, if you relied on the Bishop factor of safety, you might say that the anchorage for the wall is not adequate and more anchorage is required. On the other hand, if you were to depend and hang your hat on the Spencer method, then you might say, well, for temporary works, a factor of safety of 1.2 something is adequate. The point here is, once again, that in situations like that, it is almost mandatory to produce a GLE plot in order to see why there is such a big difference between a Bishop factor of safety and a Spencer factor of safety. I have noted in this session that the limit equilibrium formulation has some limitations, and we have discovered that to overcome some of these limitations, we can rely on finite element computed stresses. In the context of GeoStudio, we can do a sigma W analysis. From a sigma W stress method analysis, we can determine sigma x, sigma y, and tau xy in each element. So here is sigma x, sigma y, and tau xy. Once we have this stress state at a point, we can find the stresses on any other plane using Moore circle techniques. And so let us say that we have the base of a slice here. Here's an element, and here's the base of the slice. From the finite element stresses and using Moore circle techniques, we can find the mobilized shear at the base of the slice, and we can find the normal at the base of the slice. And once we know the normal, we can determine the shear strength at the base of the slice. We do this at the base of each slice, and then we add up all of the mobilized shear from crest to toe. Then we determine the shear strength at the base of each slice doing this method, and then we add it all up together, and that is the total available shear resistance. And dividing the shear resistance by the shear mobilized gives us a measure of the factor of safety. Now, I won't take any more time here to discuss this method, except to note that using finite element stresses overcomes many of the limitations in the limit equilibrium method. And as I've already noted, we don't have time here to discuss all of the details here. It is beyond the scope of this presentation and this session. And for those of you who will be part of the Sigma W workshop sessions, we will talk in more detail about how to use sigma stresses to compute factors of safety. Once again, this is discussed in more detail in the paper on the CD in the Papers of Interest folder, the 2001 R.M. Hardy lecture, The Limits of Limit Equilibrium Analyses. That gives you a very high-level view of the background and fundamentals of a slope W formulation. Several times I've noted that the limit equilibrium method has some limitations, but at this stage, without going into a great deal of detail, I'd like to note that the limit equilibrium method remains a good tool for use in practice, provided you understand the limitations. It is vitally important to understand that the method is based purely on the principles of statics. There is no other physics included in the formulation. For example, we should not expect stress-strain behavior. It is not capable of providing this type of behavior because no stress-strain law has been included in the limit equilibrium formulation. Understanding this helps greatly with interpreting slope W results. Also, it remains a very good method, but you have to be somewhat forgiving of the method's idiosyncrasies. For example, just because some unrealistic stresses show up for some slices does not, let me repeat, does not mean the factor of safety is necessarily unacceptable. And again, we should not necessarily expect that the computed stresses to necessarily represent the actual ground stresses. So if you want to be an effective user of this very powerful tool, and that we can still use it in practice, but to be an effective user requires understanding the details. Understand, for example, what makes your friend tick. To make effective use of slope W requires looking beyond just the factor of safety. You cannot simply look at the factor of safety and say, I'm done. There is more to the interpretation than that. You should, for example, look at factor of safety versus lambda plots, the GLE plot. We have looked at view slice force information. Take a look at some of the slice forces details. And also, as we will see later on, it is possible to plot various key parameters along the slip surface. This is also very useful in helping you to interpret the results of slope W. If you have a reasonably good understanding of the slope W fundamentals and the limitations, your confidence in interpreting your slope stability analysis results will soar to new heights. I would encourage you to take the time to understand some of these key fundamentals, and as a result you will enjoy using slope W more, and you will have more confidence in relying on the results for design. This brings us to the end of this session on slope W background and fundamentals.